Thanks for the invitation, and I'm happy to open this meeting. I wish we were all in Seoul, but at some future time, I'm sure we will all be in Seoul. So I want to talk today about G2 compactifications. In fact, a little more generally, if I have a Riemannian manifold, a compact Riemannian manifold, and I have special holonomy for that manifold. So what does that mean? There are a few things that I didn't get written on my notes, so I'm going to add them in handwriting. So to find the holonomy of a Riemannian metric, I should take parallel transport around a loop, and parallel transport around a loop induces an automorphism of the metric at the point P. That automorphism group should be a subgroup generally of the orthogonal group of the Riemannian manifold, maybe of dimension n. If the manifold was oriented, then it will be an SON. And in fact, any sort of geometric structure which is compatible with the metric will induce some reduction of the holonomy group. So we get, for example, if it's a Kähler metric, then you end up with holonomy in U of n over 2, and so on. So various kinds of geometric structures of metrics are reflected in this holonomy. Now, if you have a high dimensional theory, such as string theory, M theory, or even F theory, and you want to compactify that theory to a lower dimensional space to get an effective theory in that lower dimensional space, and you want that effective theory to be supersymmetric, then one thing that you will need is, so typically I'm going to take my space-time, my M, n is a bad letter, M, maybe M comma 1, to be of the form of some effective space-time crossed with some Riemannian manifold. And the Riemannian manifold should have dimension m minus k. So this is the Riemannian manifold. And if I want supersymmetry of the parent high dimensional theory to induce supersymmetry in the effective lower dimensional theory, then I'm going to need to be able to decompose spinors according to this product structure. There are more general compactifications you can do in which the Riemannian manifold might vary over space-time, and then you would need a variant of this construction, but the simplest case is just a product. And in the product case, what we need is a covariantly constant spinor field on the Riemannian manifold. Having a covariantly constant spinor field puts a restriction on the holonomy group, and there's a classification of possible Riemannian holonomy groups, and it has a couple of big families, and then it has some special cases. And the special cases are cases that have covariantly constant spinors. So this was a piece of mathematics which predated the need of physicists for covariantly constant spinors, but it was already there and ready, at least in principle, when physicists came along and requested mathematicians, could you find us some spaces with covariantly constant spinors? So the holonomy that I'm mainly interested in today is the holonomy G2, which is a 7-dimensional holonomy, but we will also have SU3, which is in 6 dimensions, SU2, which is in 4 dimensions. This chain can be extended 1 dimension higher to spin 7, but I really won't have time to talk about spin 7 today. Now, I can use those special holonomy spaces to compactify a superstring theory, a 10-dimensional theory, or I can use them to compactify M theory. And the compactification of M theory down to 3 plus 1 dimensions, the space-time that we live in, would require a 7-dimensional space. It would require a 7-dimensional Riemannian space with a covariantly constant spinor. And unless that space is a product of lower dimensional objects, it would have to have holonomy G2. So the G2 compactification is a strategy for getting supersymmetric 4-dimensional theories out of the well-known 11-dimensional M theory. There are other strategies for getting supersymmetric effective theories out of M theory and superstring theory and F theory for that matter. but I'm going to focus on the G2 compactification case today. So one of the difficulties of the scenario that I just pointed out in the previous slide is that there are features of the effective theory that we want, including non-abelian gauge symmetry and chiral matter in 3+1 dimensions. There are features that cannot be obtained if the compactifying space is a manifold. So it's been proposed that we should compactify M theory on some classes of singular spaces as well. The effective theory that we'll get is not just derived from supergravity alone, but it must contain other massless fields, such as non-abelian gauge fields or massless matter fields corresponding to some kind of physics localized at those singularities. I'm putting in non-abelian gauge fields and massless matter fields, chiral matter fields, exactly because those are the features of the 3+1 dimensional physics that I would like to model. If you want to model other features, you may need to go to other classes of singularities. But one of the challenges here is to identify which massless fields represent the new physics and link those somehow to the geometry of the singularities that we're imposing. Another challenge, of course, is going to be to find models with those singular types of singularities. So the gauge field situation is very well studied. It's understood to be derived from what are called ADE singularities. There's a classification of simple singularities in complex dimension 2, which is it'll be complex codimension 2 in these spaces, or real codimension 4. And other cases which have real codimension 6 and 7 for compactifications to 4 dimensions, and the case I'm not really talking about today, which is codimension 8 for compactification to 3 dimensions. Those cases are much less well understood. Examples are known in those cases, but in the examples, it's often assumed that the singularity is, at least asymptotically, a cone metrically. And that assumption seems to be justified on the basis of simplicity rather than on physical grounds. So on the basis of simplicity, you can make examples, but you don't know if those examples enjoy the general features that we might be hoping to model in such a construction. So, sorry, that first paragraph is a repetition. What I'm going to do in this talk is propose a mathematical framework. Actually, it happens pretty soon in the talk, for studying singular spaces which have as an open subset a manifold with a metric of special holonomy. So the framework that I've set up hopefully captures all the relevant physical phenomena that we need for understanding the effective theories in 3+1 dimensions. And we also hope it's a reasonable framework mathematically. And so for example, you might hope that limits of metrics which are at finite distance from the bulk, the general metric, the general spaces, in a Weil-Petersson type metric would always fall into this class. And that's true in the first case that I'll talk about in a minute, the case of K3 surfaces. So here's my brief discussion of the problem of gauge fields in this context. If I am hoping to get non-flat metrics with a covariantly constant spinner, the first case I will see that if I sort of go up in dimension from 0. First case I'll see it is the case of K3 surfaces. K3 surfaces have that name because they are complex surfaces, but for the application to physics, it's really a 4 manifold. And there's one diffeomorphism class of 4 manifolds with a bunch of possible different metrics. Those metrics also have compatible complex structures. There's more than one complex structure compatible with the metric, and the physics is more interested in the metric than the complex structure. So the metrics are Ricci flat. They have holonomy SU2 contained in SO4. And the space of all Ricci flat metrics we can describe. We can describe it as a locally symmetric space, and it has natural limit points in either the Weil-Petersson, which is some kind of construction relating to intrinsically to the moduli, or Gromov-Hausdorff limit, which is a construction in mathematics to find limiting metric spaces for families of metrized spaces. Those limiting metric spaces might be rather singular, but it's known in the K3 case both how to find limit points in the Weil-Petersen sense or in the Gromov-Hausdorff sense. Those limit points are the same in those two senses. And in the limit case, what happens is that certain configurations of two spheres on the K3 surface shrink to zero area in the limit. And it's known by work of Kobayashi and Todorov, which generalizes Yao's proof of the Calabi conjecture, that when you shrink those configurations of S2s to zero area, you get a metric which is an asymptotically orbifold metric on the limiting metric space. So everything works very nicely in the case of K3 surfaces, at least if you're only collapsing collections of S2s. It's a little more complicated to say what happens if if the whole K3 collapses to zero volume, but there's been progress on that as well. But anyway, for the present purposes, I really want to collapse certain configurations of S2s. Those configurations form graphs that look like AD or E graphs, which is why the ADE terminology is used. And if I compactify M theory on a non-singular K3 surface, which is close to such a limit, what I find in the spectrum there, if I'm careful, is massive gauge fields in the spectrum whose masses are proportional to the areas of the S2s that are shrinking. And so in the limit where the S2s have shrunk to zero size, I get massless fields. Those fields can be thought of as coming from the nearby smooth K3 surfaces as having wrapped M2 branes on the shrinking spheres. Of course, you can't wrap the M2 brane anymore when the sphere has shrunk, so you have to make a little bit of, do a little bit of work to understand what the effective theory is, but it all works out. So if I take a coupled theory, which is this 11-dimensional supergravity theory, coupled to certain 7-dimensional gauge fields, which are supported on the locus of those S2s, the masses of the gauge bosons should be among the parameters. And in the limit, the K3 surface will become singular, the masses will go to zero, and I will get an effective theory with non-abelian gauge symmetry. So that makes a very nice story. It can be studied. The first place it appears on K3 surfaces, but it can also be studied more generally as real codimension 4 behavior. And there's a completely different mathematical theme, which is to discuss what happens to those Gromov-Hausdorff limits. What happens when you try to take metric spaces that are limits of non-singular Riemannian metrics? And what was discovered a number of years ago by Chigurtian and Neighbor is that in real codimension 4, you exactly get these asymptotically orbifold singularities, and the orbifolds are all of the form C2 mod gamma. I should probably write that down. C2 mod gamma asymptotics. And the gamma is a subset of SU2. It's a finite subgroup of SU2. So those have an ADE classification, and those are the singularities that we get. And the metrics are from the flat metric on C2 asymptotic to those orbifold metrics. Now, K3s were nice to have. And if we really want to compactify M theory, we should probably stick to K3s. But most of that construction can be done using the Cronheimer way of talking about the C2 mod gamma singularities and ALE spaces. And you can see the basic point of the massive gauge bosons becoming massless in a limit. Most of the construction that I described can be repeated in the Cronheimer context and discussed kind of locally. And there are various ways of going from that local setup to a global setup using things like Higgs bundles and spectral covers, which I won't try to describe in this talk. The new gauge field that I got, which would be a massive gauge field for certain parameter ranges, will interact with the metric being used in the supergravity theory as well as other fields in the supergravity theory. And there's some equations of motion for the coupled theory. Those equations of motion include the equations of motion that we would have had in the supergravity theory itself, like Ricci flatness of the metric and covariant constancy of an appropriate spinor field to make sure that we got supersymmetry in the effective theory. And there will be some equations on the gauge field itself, a Hermitian Yang-Mills type equation on the gauge field. All of those are the natural equations of motion that you would impose on the coupled theory. One possible complication in this story, which is not fully sorted out, is that there may be some global obstructions to resolving the singularities. Singularities could be resolved locally. That's clear from either the Cronheimer business or a little more globally, the K3 case. If there are global obstructions, they're most likely interpreted as certain global properties of a family's type construction, maybe as an unexpected zero in a one form. There's some recent related mathematical work of Joyce and Karagiannis, which found zeros in one forms, which obstructed global resolutions of singularities. And that's a sort of thing which might happen here. This talk is a kind of progress report on what we know and what we still need to know. And one of the things we don't know is what might happen in this issue of globalizing the resolution of singularities. Okay, so that was the real codimension for singularities. The next case in which I see covariantly constant spinors is Calabi-Yau threefolds. I should have mentioned that the holonomy is SU3 in that case. And in this case, as in the K3 case, I'm relying on Yau's solution to the Calabi conjecture to make sure that I have appropriate metrics, right? I didn't stress it in the K3 case. K3s had been constructed in mathematics, both algebraic geometry and complex manifolds, long before they were ever used in physics. But the focus on the Ricci flat metrics is something that's only possible thanks to Yau's solution to the Calabi conjecture. And similarly here, we wouldn't have known that the metrics that we need exist unless Yau had solved the Calabi conjecture. But he did, and he did that well before a physicist asked for the solution. That's great. However, in the K3 case, one thing I didn't stress but could have is that one of the reasons we know so well the parameter space for K3 metrics is that everything in the K3 case, and in particular this is true of the Ricci flat metrics, can be determined by evaluating a certain collection, a certain triple of two forms which make up a hyperkähler structure on the metric. Those are the positive definite part of the two forms on the metric in question. And if you calculate the integrals of those two forms over integer two cycles, you get a point in some symmetric space, and that point determines the isomorphism class of the K3. So the periods of two forms really determine the K3 up to isomorphism. And that's what we need, for example, in the argument that we got asymptotically orbifold metrics in those appropriate limits where those two spheres shrunk down. In the Calabi-Yau threefold case, we know much less about the metrics in singular limits. So thanks to work of two people, Hayakawa and Wang, who did the work independently, we know the singularities in the sense of algebraic geometry which show up in such limits. They are the so-called canonical threefold singularities. They include the real codimension 4 ALE singularities that we had before, but there are some new singularities which have complex codimension 3 or real codimension 6. Those new singularities might be isolated, or they might be somewhere within the old singular locus where there are a worsening of the singularity type in the old singular locus. However, we don't know too much about the metric behavior of these singularities. The very simplest singularity of this type is a so-called conifold singularity. And we do know a metric for the conifold case. That metric was written down by Candelas and De La Osa in the physics literature and by Stencil in the math literature in the 80s, I think. And that the success of studying that metric may have been one reason why people tend to assume that the singularities that occur are metrically cone-like, but it's not generally true. In fact, it's been known to be false for some time. I'm giving an example of singularities. In algebraic geometry, I would describe these as x squared plus y squared plus z squared plus t to the k equals 0 with x, y, z, and t complex variables. That's an isolated hypersurface singularity of a threefold. However, there are no cone metrics, Ricci flat cone metrics on that singularity when k is at least 3. That was proved by Gauntlett, Martelli, Sparks, and Yao some time ago. And a little more recent is the existence of non-cone metrics, which are Ricci flat, for k at least 4, due to Hein and Nadel. The k equals 2 case is the conifold that I already mentioned, so that was already known. And the k equals 3 case is not covered by their results, so that's still partially open. So we don't necessarily have cone metrics. That's part of our problem. If we had appropriate metrics, we might, again, think of capturing the physics content by adding some fields. In the gauge symmetry case, I added 7-dimensional gauge fields. Here, because of the codimension of the singularity, I'll add 5-dimensional fields, and they should be scalar fields corresponding to shrinking some S2s in a Kreppert resolution of singularity with wrapped M2 branes. That's one class of such singularities. But unfortunately, that's not enough to fully understand the situation. So that explanation of wrapping M2 branes on S2s fails to be complete in 2 ways, or for 2 reasons. One is that I might be shrinking a complex divisor to a point. And in that case, the physics that I would get, if I'm compactifying M theory on a neighborhood of that divisor, the physics that I will get is a conformal field theory in 5 dimensions. And more generally, if I've included that divisor into a more general Calabi-Yau, I'll have an effective theory in 5 dimensions, which looks like a gauge theory, but it will be coupled to this conformal field theory in 5 dimensions. And the physics of that, either isolated part where I've decoupled the conformal field theory, or the conformal field theory itself coupled to the rest of the structure, is much more complicated and can't be described just in terms of shrinking S2s. I've got a larger space which is shrinking. I can have the ability to wrap M5 branes on that space and get effective strings in the spectrum. There's a lot of complication. So that's point number 1. Point number 2, not every canonical threefold singularity, which is a notion in algebraic geometry, admits what's called a Kreppert resolution. Kreppert resolution means a resolution that does not disturb the triviality of the canonical bundle. So to be a Calabi-Yau threefold and a singular Calabi-Yau threefold, I should have some analog of my holomorphic three forms, which essentially would be given by holomorphic three forms on the non-singular part. And I should ask whether the blow up that I'm trying to do to describe the singularity respects that holomorphic three form or not. And sometimes it doesn't. Sometimes the only way to get the singularity to resolve is to allow zeros or poles in that previously holomorphic three form. So sorry, previously it was nowhere vanishing. Now it might have zeros. So if it has a resolution with no extra zeros, we'll call that a Kreppert resolution. The discrepancy is the possible zeros or poles, which is the origin of that term. But in general, for a threefold, you might have to deal with something called Q factorial terminal singularities, which are the ones that have no Kreppert resolution. A particular example of such a guy is the k equal 3 case in my family of examples on the previous slide. That was the one where I didn't have a complete answer to the metric situation. So that's a really interesting type of case to study, is what are the appropriate metrics? What are the limiting metrics on Q factorial terminal singularities? and how do we extract the physics from that situation. Those spaces have been studied in physics by Grassi and Wiegand, and some kind of physical description can be given, but I think the story is not over there, and there's something very interesting to be uncovered still. In any event, middle of that slide, in any event, I'm associating some kind of 5-dimensional matter fields to shrinking spheres, or maybe something more complicated. I can do that in families. And again, the local analysis of the singular type should tell me what kind of 5-dimensional matter fields or fields realizing the CFT I need to put in. And as in the gauge field case, there might be global obstructions to resolving the family of singularities, even if I can resolve them one at a time. And that might be analogous to the zeros in a one form as encountered in the work, slightly related work of Joyce and Karygiannis. Okay, so finally I get to the part that's sort of most relevant to this talk, which is holonomy G2, which applies in the 7-dimensional case. So I remind you that G2 is a subgroup of SO7. It has a natural 7-dimensional representation. And when I speak of holonomy G2, I actually have that representation in mind. So I have a 7-manifold, or perhaps a singular space that is generically a manifold, and I would have a metric on the generic part. It would have some kind of asymptotic behavior near the singularities, and I would insist on G2 holonomy in the non-singular part and appropriate asymptotic behavior near the singularities. But I'm on even shakier ground for understanding what those codimension singularities might do. It's known that you have to go to those codimension singularities to get a chiral spectrum, and we in 4 dimensions, and we're expecting a chiral spectrum in 4 dimensions. So if we were just to consider the codimension 6 singularities from the previous slides, well, I would have a whole 1-parameter family of those codimension 6 singularities in this context. That 1-parameter family would be a bunch of circles. Having the singularity on a circle essentially means, when I do the reduction on the circle, that I got both chiralities of singularities showing up in the ultimate compactification to 4D. So I can't get chiral matter from codimension 6. I need to go to codimension 7. And I really don't understand the metric in this case. Again, there are a number of examples that have been found in which the codimension 7 phenomena is a metrically conical point. Metrically conical means that it's dr squared plus r times something or other, right? So it really looks like the metric on a cone. But there seems to be no good reason to assume that the only singularities that are relevant here are metrics that have, are geometric singularities that have conical metrics. The experience with metrics in the Calabi-Yau threefold case suggests is probably not true, right? I could write down some very simple looking spaces there in algebraic geometry which don't have conical metrics. So it'd be great to have a classification of such singularities and of the resulting effective physics, which we could model by essentially 4-dimensional physical fields associated to the singularities. We don't have that classification yet. We don't really know, aside from a few, basically handful of examples. But even without an explicit classification or a full understanding, we still might end up getting information about the structure and give some kind of mathematical description, which could be sufficiently detailed for further study and for the construction of global examples, which we don't really have. So the basic structure that I would like to study is a 7-dimensional space which has singular sets of codimensions 4, 6, and 7. Some of those singular sets might be several components worth of singularities, and some of those components might be contained in other loci. So for example, in codimension 6, we already pointed out that there could be codimension 6 singularities which were away from the codimension 4 stuff, or codimension 6 singularities which were slight worsenings of singularities in codimension 4. I should point out that because codimension 4 is responsible for non-abelian gauge symmetry, if you're studying a physical phenomenon which is charged under non-abelian gauge symmetry, it better be, the singular locus had better be contained within that codimension 4 locus. So interesting cases include codimension 6 and 7 singularities, which are inside the codimension 4 locus, because that will allow for singularities which are charged under the non-abelian gauge group. But there might be singularities which are uncharged under the non-abelian part, could be charged under some abelian part. There are other sources for abelian gauge symmetry in this context. So a general setup will allow different components of those loci. Away from the singular locus, I should have a metric with a covariantly constant spinor field. And that spinor field should have reasonable behavior near the singular locus so that it can be interpreted as the along the fiber spinor component of the spinor when I'm doing the reduction down to a supersymmetric theory in lower dimension. And typically I've sort of emphasized, for example, the non-abelian gauge field, but that non-abelian gauge field is really supposed to be part of a gauge, a supersymmetric gauge multiplet in the effective four-dimensional theory. So it's going to come along with other things. And the full dictionary of how this structure works out would include those remarks. One possible way of modeling these things would be to remove small neighborhoods of connected components of the singular locus. Then we would have a set fibered over a 3-manifold with fibers being small 4-balls monofinite group. That's what we're removing for the codimension 4 stuff. A set fibered over a 1-manifold with fibers being small 6-dimensional neighborhoods of canonical 3-fold singularities. That's what I would remove in the Calabi-Yau 3-fold case. And small 7-dimensional neighborhoods of codimension 7 singularities. Since I don't really have a good way of getting a handle on all of those yet, I would just be able to make that statement at the moment. And then I would get some information about the physics from the boundary of the removed set. So if I take appropriate kinds of differential forms on that boundary and do integrals of those differential forms, I can capture a number of the physical features of the removed set. If I thought that the removed set was responsible for things like gauge symmetry and matter, then I would definitely expect from standard geometric approaches to gauge symmetry and charged matter to see such a formulation in terms of differential forms on the boundary. In fact, there are a small handful of known types of codimension 7 singularities which work in this context and create chiral matter. And Witten was able to measure the chirality of the matter of those physical fields by doing appropriate integrals over the boundary. So one could hope that, okay, that slide got cut off. One could hope, well, I wonder what I wrote. One could hope that that works for all cases in codimension 7. Sorry about that. So what do I have to say about constructions? Well, in the case of K3 surfaces, there were many constructions known for K3 surfaces based both on algebraic geometry and complex manifold theory. They were known long before questions were being asked about these spaces in physics. And although those questions and answers, although the properties of those constructions were phrased in terms of algebraic geometry and complex manifold geometry, thanks to Yau's proof of the Calabi conjecture, we also understand them from a metric point of view as well. So we're in pretty good shape for constructions of K3 surfaces. For Calabi-Yau 3-folds, Yau's theorem reduces the study of Calabi-Yau 3-folds to algebraic geometry. Every Calabi-Yau 3-fold is has an underlying algebraic variety, in fact, a projective variety. And Yau's theorem guarantees that appropriate Ricci flat metrics exist on such projective varieties. And so in principle, the problem of finding all such spaces could be solved in algebraic geometry. That problem has been around for a long time, 40 years, and it hasn't been solved. So saying that it can be solved in principle is a great statement, but somehow my algebraic geometry friends and I have not succeeded in solving it. We have lots of examples. There are lots of interesting databases of Calabi-Yau threefolds. People have used those databases to learn about structures of large groups of Calabi-Yau threefolds, but it's really not known if the things in those databases, which I'm referring to, complete intersections and toric varieties, for example, it's really not known how general among all Calabi-Yau threefolds those particular examples are. So statistical study of those guys, while somewhat worthwhile, since we don't know that the sample is representative, we have to be a little cautious about extrapolating results. However, in the case of holonomy G2, the situation is much worse. So I was complaining a little bit in the previous paragraph about Calabi-Yau threefolds, but in the case of 7 manifolds with holonomy G2, much less 7-dimensional spaces, which aren't manifolds of holonomy G2, situation is much worse. The local existence of metrics with that holonomy was unknown until the 1980s in some work of Bryant. And the first compact examples were constructed in the 1990s as desingularizations of toroidal orbifolds. What's a little bit ironic about that is that the toroidal orbifolds themselves have the singularities of the types we're now looking for, and they're the first examples of compact spaces with non-abelian gauge group type singularities if we compactify just on the toroidal orbifold itself. Of course, metrically, they're not as interesting because the metric is flat. I didn't need Yau's theorem to get a metric of the right kind. Now, there's been a fair amount of activity in the study of manifolds with holonomy G2 from the mathematics side in the last 10 years or so because of a thing called the twisted connected sum construction. And this construction glues together two spaces of the form Mi cross S1, where Mi is a non-compact algebraic variety of dimension 3, I should have said. Well, it's pretty obvious because I'm forming a 7 manifold. It's complex dimension 3. Of a certain type, it's a Fano variety or a non-compact subset of a Fano variety, a Zariski open subset of a Fano variety. And there's significant mathematical work that you have to do to ensure that when you glue together the spaces, you get a metric with holonomy G2. You can build metrics whose holonomy is within G2 on both pieces, but then getting them to match up properly when you glue together is a problem in analysis, and it's a pretty challenging problem in analysis. So I've got some work in progress, various pieces of which are in collaboration with various different people. So I've decided not to try to name them all, but I'm extending this construction to allow for singularities of appropriate types. So the Mi, those non-compact algebraic varieties, Zariski open and Fano threefolds, should have ADE type singularities on a set of complex codimension 2. I'm crossing that with S1, so I'll get the same phenomenon of real codimension 4 in the 7 manifold. And then when I glue them together, then I don't want to just take the product Mi cross S1 because that would not allow for the codimension 7 singularities. Instead, I should take an appropriate bundle in which the S1 collapses to points at a few isolated points on the M1, on the Mi, excuse me. And that will allow for some singularities of real codimension 7 to show up in this process. And then, of course, one also has to generalize the analysis to allow for the Mi to have some singularities when you're gluing things together. So there has been some progress on each of those aspects of the construction, but there's nothing yet in writing because there's no real result that one can point to yet. But I'm pretty confident that something like this is going to work. And maybe I can report back on that at some future Strings and Soul meeting. So I guess I'm a little short of time. Started late, but I'm finishing on time. I'm not sure how that happened. We can have more time for questions. So our understanding of singular spaces with holonomy G2, and in particular of the codimension 7 singularities, is quite unsatisfactory. But there's a general framework which we can build, which has a chance of capturing all the phenomena that we need to determine the effective theory in 4 dimensions. And the hope is that this framework will lead to further progress in constructing local and global examples and understanding the physics of those examples. Ultimately, as in the Calabi-Yau threefold case, one would like a complete classification, both of the singularities that could occur and of the global ways of building holonomy G2 spaces, which would enable one to study all such compactifications. And I will end my talk there and take questions.
Thank you very much for the very nice talk. Yes, Pyoljin, questions?
Yeah, I was just wondering, I mean, I remember like 15, 20 years ago, there was some flurry of activities, especially on G2, centered around phenomenology-oriented people. What were they? Do you know what those were? I mean, relative to what you are trying to do here?
Right. So when I mentioned that Witten managed to calculate the chirality in certain codimension 7 examples, that was part of that thing that was going on. There were a number of examples constructed, a number of calculations that were made. They tended to be local rather than global, and we didn't have techniques for assembling those local constructions into global examples at that time. We have better techniques now, but they haven't really been carried out yet. So I would say that the phenomenological work, let me make a general comment. The general comment is that in the case of Calabi-Yau threefolds, when I see a singularity that I've identified in algebraic geometry, then I'm typically able to decouple the fields represented by algebraic functions that belong to the singularity from those that belong to the bulk. But I don't have a technique for doing that in the G2 context. So it was great that people did this local work, but I have no direct way of plugging the local work back into more global examples. I think that's what I will say about that flurry of activity.
Okay, other questions?
So in local case, I guess for C2, we have SU2. We look at the finite group of SU2, then divide C2 by those SU2 sub-finite groups.
That's
Is
right.
there something similar on G2 case where we are looking at finite group of G2 and dividing G2, say R7 divided by that finite groups?
No. So the toroidal orbifold construction that Joyce worked out, he was looking for subgroups of, basically subgroups of SO7, which might preserve a G2 structure. And he found a collection of examples which are all abstractly isomorphic to Z2 cross Z2. There have subsequently been some generalizations of that, but there's no general classification of which finite subgroups, which orbifold type groups you might be able to use to preserve a G2 structure. That's all you really had to preserve in the C2 case was a holomorphic 2 form. So it was pretty easy to check that SU2, which and the S in the SU2 makes it preserve a 2 form. Then, you know, the list of such singularities, such finite groups, excuse me, is 150 years old. That had been classified a long time ago. Oops.
Okay, other questions?
So for say C2 case, for ADE case, if you go to global, then you have to have a K2. But I heard there is something in between where if you think of, instead of ALE space, if you think of ALF, which is roughly S1 cross R3,
Right.
then I heard that there is no E-type singularity. Maybe there's some, so you don't have a ALE space, ALF space for E-type singularity. So that's some sort of global obstruction, I guess, sort of small global. So I was wondering whether there's that sort of game also for, say, C3 case or R7 case. There are certain type of singularity you cannot extend to, say, ALF, even though it's sort of ALE.
Right. So here's how I would interpret that result about ALE and ALF. If I look at an ALF space, then I should have a circle action as well as the finite group action. And that means that I have essentially a small circle in the K3 manifold that I'm trying to model, or a local version of K3 that I'm trying to model. And in fact, the limits that I will get that involve ALF singularities are limits in which the entire K3 collapses because that circle is collapsing. There's also ALG, which has a 2 torus in the fiber, the 2 torus acting on the whole thing. And in the ALG case, if I collapse, I'll actually get an entire family of 2 tori in the K3 going to 0 size. So the ALE, a small neighborhood of an ALF singularity is an ALE space. If I take a small ball around it, is an ALE space because I've removed part of the circle. But if I look at the global structure of the singularity together with the S1 action, then I see that it had to be an ALF space. And indeed, some of the ALE singularities do not extend to ALF. So in this context, I would say, you know, I didn't really explain this too much, but one thing that happens in this twisted connect sum construction is that the space MI has a K3 fibration. And what I'm going to do, what I'm in the middle of doing to generalize that is to allow the K3 fibration to be generically singular. So I will allow A1 or A10 or something within the K3s, and it'll have some generic value as you go across. So I'm expecting to only shrink down the corresponding S2s, which would give me enhanced gate symmetry. But if I tried to take a limit of the G2 manifold in which there was some circle that also shrunk down, then I might get some ALF spaces as well. And there could be interesting limits of G2 manifolds which had ALF singularities instead of ALE singularities because I was collapsing another part of it.
Mm-hmm.
Or ALG for that matter, ALF or ALG could happen.
So the TCS construction by itself doesn't allow for codimension 7?
That's correct. I mean, mathematicians were excited that they had a way of building manifolds, right? And so TCS was all about manifolds. And as I mentioned, there is this delicate mathematical work that you have to do, which is mathematical analysis to prove that you got a G2 metric when you glue things together. And so if you're going to glue things together in a way that creates singular points, then you don't have the same tools available because you're now dealing with a space that's not a manifold. So you can't sort of invoke the standard methods of analysis to do your work for you. You have to modify it somehow.
And then you're saying in your work in progress, by shrinking the circles non-generically, you can achieve this roughly?
So let's see. So what I'm going to do is take my MI, which is a threefold, which has a 1 parameter family of K3 manifolds on it. And I'm going to replace that with a singular MI in which I've allowed each of the K3s in that family to itself have the ADE, some kind of ADE singularity. So that will give me a singular space. I also will need to modify the S1 into a generalized bundle in which at finite collection of points, the S1 shrinks to a point. And
Right.
at those points, I have the potential of putting in codimension 7 singularities.
Right.
So I can construct those pieces, but the thing that is stopping this from being a finished work is that I now have to modify the mathematical analysis argument about why you can glue together and get a G2 space.
Right. Okay. Any other questions?
Yeah, so is there any natural plane construction for local case for some type of singularities?
I'm sorry.
Is there
which
any
kind of
plane construction for G2 singularities? I mean, 5D case, there is a PQ5 brane web, which is sort of naturally capturing open Calabi-Yau space.
Right. I don't know. That's a good question. I don't know. It's probably worth looking at.
Okay, if there are no further urgent questions, why don't we at least officially close the session?